In this session, we'll be discussing section 2.3, parametric surfaces and surfaces of revolution. So as usual, I'll be giving solutions to the problems I have prepared in here. I expect that you have watched the lecture videos associated to this topic. So let's get started. First problem here. So identify the surface given by this vector valued function r of u comma v, which is u comma cosine v comma sine v. Okay, so this is a vector valued function, and this is with two variables. So you expect that you will get a parametric surface. You will get a surface. So let us start. If you have, this is your x, this is your y. So this is your x, this is your y, and this is your z. So we have these parametric equations. Okay. So x equals u, y equals cosine v, and z equals sine v. Okay. Now, for any point x, y, z on the surface, okay, observe that you can have y squared plus z squared. Okay, so y squared plus z squared, you will get cosine squared v plus sine squared v, and of course identity, this is equal to 1. Okay, so in here you have y squared plus z squared equals 1. So at least on the yz plane, it should look like a circle. Okay, and then on the x, it means that it can be any u. Okay, and this means that for a constant x, the cross sections parallel to the x-axis are circles of radius 1. Okay, therefore, if we have we try to sketch it, we will have this circular cylinder. Okay, so right circular cylinder. So notice you have this x-axis is going that direction, y-axis going this direction, and then z-axis going up. And then if you look at, so if you can just view this x, y, z, you should see a circle. Okay, if you are looking at this view here. Okay, and maybe we can try to see the graph using GeoGebra, and we'll see you can we can rotate the axis, so we can easily see this surface, or at least we'll have a nice view of this surface. Okay, so let's see, we have here, let me share my GeoGebra, share screen, we have this one. So we will have the surface y squared plus z squared equals 1. So as you can see, your red axis here, that's your x-axis. The green axis here, this is your y-axis. The blue axis here, it's your z-axis. So if you look at the front, okay, if you are in front here, so you have your z and y plane, so you should see this circle here. Okay, and this cylinder here, right circular cylinder here, it's parallel to your x-axis. Okay, so let's go back to our slide in here. So questions. for our first problem. Let's consider this next problem here. So in here, describe the parametric surface given by the parametric equations. X equals u cosine v, y equals u sine v, and z equals 4 minus u squared. And then let us identify the grid curves with constant u and grid curve with v equals 0. So remember, when you have the grid curve, it's like you are drawing the traces on the surface. Okay? So first, let's see what these parametric equations here represent. Okay? So first, you can eliminate the parameters u and v by, of course, you can get the square of x plus the square of y, okay? And then you will have this guy here, okay? U squared cosine squared v plus u squared sine squared v. And then you can factor out the u. It's a common factor, okay? It's a common factor, and therefore, you will have u squared times cosine squared v plus sine squared v. But then again, cosine squared v plus sine squared v, that's equal to 1. Okay? So we'll end up with x squared plus y squared equals u squared. But we still have the u in here. Okay? We can use this equation here. Z equals 4 minus u squared. Let's isolate the u squared. Okay? So we can replace this u squared here by the following. 4 minus z. And therefore, we will have x squared plus y squared, which is equal to u squared. And using this, we will have 4 minus z. Okay? Or we can rewrite this as z equals 4 minus x squared minus y squared. Okay? So if you look at this, you see, if you cover the z, if you cover the z here, you will have a circle of radius 4. Okay? So if you change your z, if z is less than or equal to 4, you will have a circle. Okay? Now, if you instead let y equal 0, then you will have z equals 4 minus x squared, and that's a parabola. And then if you cover this x squared here, you will have z equals 4 minus y squared, and that's again parabola. Okay? So you will have a paraboloid. Okay? So that's a paraboloid. And from your Cal 2, you can sketch this paraboloid. Okay? But let us look at the grid curves. Take note that with constant u. So u is fixed. Okay? U is fixed. And then z will be equal to 4 minus that fixed u. Okay? Z minus 4, z equals 4 minus that fixed u. Okay? And you'll see those circles. Okay? So if u equals u naught, which is a constant, you will have here z equals 4 minus u squared. This is constant. And therefore, you'll just have this guy here. So it's a circle. Okay? On the other hand, well, yeah, it's in here. We have circles parallel to the xy plane. Okay? On the other hand, if v equals 0, so what happens? V equals 0, sine v here, that becomes 0. And then here cosine 0, that's just 1. So it will mean what? X equals u. Okay? X equals u. So v equals 0, you will have sine 0 equals 0, and therefore your y, it's equal to 0. So this will disappear in your equation. So if v equals 0, the parametric equations will be this guy here, x equals u, y equals 0, and z equals 4 minus u squared. Since x equals u, this u squared, we can replace that with now z equals 4 minus x squared, which means that it will be a parabola. Okay, opening downwards with peak at 4, z equals 4. Okay, and that parabola lies on this y equals 0. So it will be on the xz plane. So if we look at that, we have this parabola and on the xz plane. So this will be the sketch. So in here, you see this blue part here. Let me change that. So you have this part here, it's going around. Okay, so these are the circles that you see for the for constant u. Okay, for different constant u, you will see that circle. On the other hand, on the xz plane, so you see this red guy here. Okay, of course, this is one side of the parabola, and then the other side is towards the back side. Okay, so we have this grid curves. Okay, so questions. Next problem. Now, this time, we want to give a set of parametric equations for the surface obtained by revolving y equals e to the x. About, first, you have the y-axis, and then the x-axis, and then the other one, you have the y-axis. Okay? So in your calculus 1, we did something like this. We wanted to get volumes of solids of revolution. Okay, I'm not sure if you've reached finding the surface area of a surface of revolution in your Cal 1, but anyway, you have a plane curve on the xy plane, and then you revolve it, you will get a surface. So you just have the plane curve. Okay, you just have the plane curve. So when you do the revolution, only the points on the curve will be revolving about the axis, and therefore generates a surface. Okay. So for the first one, remember from your Cal 2, we have your generating curve y equals e to the x. Okay. So you can write this as y equals f of x, and therefore the surface of revolution is given by this parametric equations. So you can let x equals x, y equals e to the x cosine theta, z equals e to the x sine theta. Okay? If you want to use other parameters, maybe x equals t, y equals e to the t cosine theta, z equals e to the t sine theta, that's totally fine. Okay? And then if you course, if you try to sketch this, you will get this surface in here. Okay? So you have your, again, the orientation. This is your positive x-axis. This is your positive y-axis, and that's your positive z-axis. Okay? You have y equals f of x. Okay? So you have e to the x. So if you look at the x-axis here and then the y-axis here, okay, so this is your x, this is your y. You have y equals e to the x. So how are we going to graph that? So this is the back part. That's the negative side of your x. The graph will be something like this. So you have here and then something like this on the xy plane. So if you revolve about the x-axis, this is what you're going to create. Okay? On the other hand, let's have the guy here. Suppose the axis of revolution is y-axis. Okay? So we rewrite this y equals e to the x in the form x equals ln of y. Okay? In the form x equals ln of y. So that will become our generating curve. X equals ln of y. And then you will have the generating curve. And if you write the surface of revolution, the parametric equations, you can have x equals ln of y cosine theta, and y equals y, and then z equals ln of y sine theta. So in here, it may be confusing, but take note, your ln of y here, okay, is multiplied to the cosine of y. It's not y being multiplied to cosine theta only, or y being multiplied to sine theta only. So it's the logarithmic of y being multiplied to cosine theta or sine theta. Okay? Now, the graph. So just like in here, you have this, okay? You have this graph in here and you revolve about this. So this time, if you revolve about the y-axis, so this is your axis of revolution, okay? You will obtain the following sketch here. Okay? So let us see. So again, what is this? You have your y. This is your x. Oops. This is your x-axis. This is your y-axis, and this is your z-axis. Okay. And what do we see? So you have here y. So again, this is still the generating curve. That's still your x equals ln of y. Okay. So you have this part here. It's not clear in here, but the thing is your x. So the graph would be, if I try to graph it, it will be this guy here and then this part here on this side. Okay. Okay. So again, this is your x-axis. This is your y-axis. X, y in here. Again, this is the back part of your x. So this is plus, minus. So the graph, it's still like this. Okay. So if you revolve this, there's a fixed point at this point here. There is a fixed point at this point. And that's this guy in here. Okay. So that's this guy in here. So it's that one. Okay. And of course, if you revolve this, this will be very, very wide, this part here. Okay, and then as this increases here, the cup that will be revolved or that will be constructed there, it's it's small, so it will have something like a wide base because of this part after the revolution. Okay, questions? So on our from our first problem, we had um, identification of the surface if we are given the vector valued functions. Okay, and our second problem, identification of the surface, still if you have this parametric equations. Okay, and then for the third problem, uh, we had we had um, construction of surface of revolutions. Okay, of course you can write a set of parametric equation. So you are asked to give a set of parametric equations. Okay, so for our last problem here, we'll consider working on tangent planes. So in this problem, we want to find the equation of the tangent plane to the surface given by x equals sine v, y equals v minus 1, and z equals e to the u at the point p sub 0 of, at the point p naught with coordinates 0, -1, and 1. So to find the tangent plane, you need the vector valued function representing this parametric surface. So you'll just write your r u comma v if you are going to use the parameters u and v, and then you will need the first partial derivatives, so with respect to u and then with respect to v, so remember that, and then you will need the cross product in order to get the normal vector, okay, to the tangent plane. And then you're done because you have the point here. So let's do that. So first, the point P naught, it's generated when u equals v equals 0. Okay, so when u equals 0, v equals 0, sine 0, that's equal to 0. Y equals 0 minus 1, that's -1. Z equals e to the 0, and that's +1 in here. Okay, so we solve for the partial derivatives with respect to u and with respect to v. So you have here, so again, if you write your r of u comma v as sine v comma v minus 1, comma, and then e to the u, okay, we'll get with respect to u, partial derivative with respect to u, this is 0 because there's no u in here. Also this one, this will be 0, there's no u in here, and you only have this e to the u. So that's our partial derivative with respect to u. And then if we do derivative with respect to v, you have the derivative of sine v, which is cosine v. The derivative of this is just 1. And then for this will disappear because it does not have any v. So if we evaluate at the point u equals v equals 0, you'll just have the point 0, 0, 1 for the partial derivative with respect to u. And then for r sub v, you will have cosine v, comma 1, comma 0. And then again, evaluated at the point 0, 0, meaning u equals 0, v equals 0, we'll just have the point or the vector 1, 1, 0. Okay? And then we get the cross product of these two guys here. The normal vector tangent to the plane at this point here, so 0, negative 1, 1. So it's you can get that via the cross product of these two guys. Okay? Take note that partial derivatives, okay, that gives the vector parallel to the tangent, okay, parallel to the tangent plane. It gives you the tangent line, okay. The vector here gives you the direction of the tangent line for fixed v, so along u, and then in here the direction of the tangent line for fixed u, so along that direction. So you have those two parallel vectors to the tangent plane. The cross product will give you a perpendicular vector, which will then serve as the normal vector. So we get the cross product, and we will end up with this. Okay, remember, getting the cross product, it's just the determinant. Okay, first row, it's your ijk. Second row, it's your first factor here, and then the third row, it's your second factor here. So you can get the cross product. You will have, so at I, so you have this and this, so that's negative 1. So 0 times 0 minus 1 times 1, that's negative 1. For the j, you also get positive 1. So this is your j. You have this and this minus this times this, but you negate. Take note that at the middle you have negative of that. So that's why you will get positive 1. And then for the k part, for this 2 by 2 matrix, it's just 0. Therefore, the normal vector will be negative 1, 1, 0. Therefore, you have the normal vector, you have the point. You can write the point normal form of the tangent plane. Okay? And then after you simplify that, you will have this equation. Okay? So again, point normal form, you will have negative 1 times x minus 0 plus 1. Let me just rewrite this whole thing here. So negative 1 times x minus 0 plus 1 times y minus negative 1 plus 0 times z minus 1 equals 0. So if you simplify this, you will end up with this expression. So minus x plus y plus 1 equals 0. So that will be the equation of the tangent plane.